This program is brought to you by Agnes Scott College. For more information about Agnes Scott College, please visit our website at agnesscott.edu.
She completed her undergraduate degree at Tennessee Technological University, went on then to Vanderbilt University, where she received a PhD in physical chemistry in 1997. She was then a postdoctoral fellow at Colorado State University from 1997 to 99, before coming here to Agnes Scott College in the fall of 99. The past year, while on sabbatical, she went back to Colorado State in beautiful Fort Collins, which you should go and see if you've never been there. It's around the edge of the Rocky Mountains, beautiful place, where she worked with Nancy Levenger and Randy Bartel, and her talk will be directed towards her research project, and it's titled Good Vibrations, a New Tool in the Analytical Chemist's Toolbag. So please join me in welcoming Ruth.
Well, thanks, everybody. I appreciate you coming. I just will tell you up front, I wish I had more data to show you, but I do have a project to show you, so I'm excited about being here today. So, I tried to have a catchy title to draw people in. I hope it's excited you. Basically, I want to talk about a new tool that's being developed in Randy Bartel's lab at CSU. He's actually in the, what is it? It's the Electrical and Computer Engineering Department at CSU, and he's building a number of different types of lasers, but one of the lasers that he's building is a fiber laser that, that I am hopefully going to be able to use. And so it's a collaboration with Randy and Nancy Levenger, is that we've got this new tool, now what are we going to do with it? And so my contribution is coming in actually looking for something to shoot the laser at and actually showing that this laser can be used for something productive, right? Chemistry, haha. So good vibrations, why did I put that up there, haha. The fiber laser is actually an infrared laser, and an infrared wavelengths, molecules that are vibrating absorb in that region of the electromagnetic spectrum. So I'm interested in studying these vibrations of molecules. So hence, hopefully at the end of the talk, you'll feel like it was good. Okay, I'm getting silly now. Just to note, the real title of my talk, if you were at CSU or someplace else, would be, it's basically what I'm doing is I'm doing a study of intermolecular interactions between two large molecules, fairly large molecular molecules, using spectroscopy where I pump with a laser pulse and then I probe with this new fiber laser that's in the IR region. Okay? And the picture, just so you know, it may look kind of distorted because I did stretch it out this way. But this is Bear Lake at Rocky Mountain National Park, and you're looking towards the mountains towards Denver. So, I mean, towards Boulder. Yeah. Amy, thank you. All right. So, a toolbox. As an analytical chemist, I think about the tools that I use to make the chemical measurements that I want to use. And so lasers are very important in our toolbox. Actually, lasers in the last 25, 30 years have become invaluable in a lot of people's labs. And so I just wanted to kind of up front tell you some exciting things that are happening with lasers in chemistry. And specifically in the last 20 years, there's been 2 Nobel Prizes that have been awarded because of work that's been done with lasers. And so, for one example, is lasers can be used to directly observe chemical reactions on the time scale of which the reaction actually occurs. And in 1999, Ahmed Zewail actually received the Nobel Prize for his work using femtosecond lasers to study these chemical reactions. And this picture is big and hairy, and I don't want to spend a lot of time on it, but I just wanted to point out a couple things. That he studied a chemical reaction in a molecular beam where he actually took molecules and had it fly through a vacuum. And this apparatus right here, the picture of it looks like this. It's a big stainless steel type of apparatus, and there's a vacuum inside, and you have molecules fly through that vacuum area. And then what he does is he brings in two pulses. One is what he calls his clock pulse, which is a femtosecond pulse from a laser. Now, what do I mean by femtosecond? Well, everybody knows what a millisecond is. A millisecond is 1/1000 seconds. A nanosecond is 1/1,000,000,000 seconds. A nanosecond is a lot more. So microsecond, we say it's 10 to the minus third seconds. A nanosecond is 10 to the minus ninth. A femtosecond is 10 to the minus 15. So it's a very, very short time these pulses of light come out. It's actually on the time scale of which molecules vibrate. And so you can actually probe the reaction in real time. It's like taking a camera and going click, 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 and watching the reaction happen with these laser systems. And using femtosecond lasers, oh my gosh, it's opened up to a wide field, a lot of different studies. You can study reactions in gas phase and condensed phase. You can study biological reactions. You can study chemical bonding, molecular size, molecular states, a wide range of things you can do with these type of lasers. Okay. Another important contribution specifically to analytical chemists who want to analyze molecular molecules, specifically looking at their structure and being able to identify them, is a technique called soft desorption ionization. And it was, and actually in 2002, one of the Nobel Prize winners in chemistry that year of 3 was Koichi Tanaka. And he actually works with Shimatsu Corporation, which is a corporation that builds chemical instruments. And the technique that he developed was to actually take a sample that you wanted to look at, say it's most commonly like a biological sample. It could be proteins, it could be DNA, it could be cells actually, and you adsorb it onto a surface with a matrix. The matrix could be the surrounding cells, it could be the blood that's surrounding something. But in the most part, it is more of a viscous type phase or a solid that will absorb the light from a laser that's being directed towards the sample. And so what you do is a laser strikes the sample, and then the sample takes up the energy from the laser, and it basically blasts small bits of the sample into the atmosphere. And these blasted bits are hopefully the analytes, the things that you want to look at. And these analytes are molecules that are going to have low charges, so they're going to be charged either positive or negative. And then they're being pulled towards a vacuum area. And they pass through an electrical field that kind of accelerates them into the vacuum area, and then we can actually look at these molecules based on their mass and their charge and identify them. And we can actually blast them into even smaller pieces so that we can get information about their structure as well. And so it's an important technique in analytical chemistry. And two specific contributions that this technique has made to the field is, one is in the study of malaria. We can actually detect malaria, the pesticides, not the pesticides, sorry, the, oh my gosh, the, what did you say? Pathogens, yes, the pathogens, thank you, ha ha ha, that causes malaria in the blood by taking a blood sample, putting it on this matrix, using this technique, and actually by using a laser that will specifically be absorbed by hemoglobin, you can blast these pathogens into the atmosphere of the chamber and actually analyze and have an early detection of malaria in the blood with this technique. It also has been very important in the development of new techniques to detect different types of cancers. Again, the cell itself can absorb the energy and be blasted into the instrument, and we can actually detect cancer cells versus regular cells using this technique. Okay? So I hope I've convinced you that lasers are making a big impact in our field right now. So what about my laser? What am I interested in? The laser that Randy Bartles has built in his lab has many parts to it, as you can see, this big looking diagram, but I hopefully will point out some important things about it. One is that it is a fiber laser. This is the oscillator part. What he does is he uses a fiber. It's a silica type fiber that's been doped with uridium. Oh yeah, I can't say that either. Sorry. And yeah, thank you. I need to calm down a little bit, aren't I? And it's pumped just with a standard diode laser. You can buy them for about $3,000, $4,000. And a picture of this, just the fiber itself, is actually down here in the corner. This picture didn't come out too well, but this is actually a laser table down here. And sitting on the table is this cords of the fiber itself. And we're actually putting in this little green diode laser. It's about this color that the laser pointer is, and it's actually going into the fiber. What the fiber does is it actually causes these pulses to be emitted from the fiber. The pulses are in the femtosecond region, and they come out at, what? I think like about 150 microns, or 1.5 microns. But we have to take the laser pulses and we put them through basically an amplification system so that we get out pulses in the end that are in the 3 to 10 micron region, which is in that IR region of the lasers, of the electromagnetic spectrum. And they have a rep rate of about 600 kilohertz, so they're coming out fairly quickly, and short pulses, 200 femtoseconds. And one of Randy's graduate students has been working on building this laser system for about 2 years. He's just finished characterizing it while I was there, and it looks like it's going to be a wonderful laser to use specifically to get femtosecond light in this region. The other thing I want to say about this laser is that a normal laser system for a femtosecond, to purchase it, it's about $100,000 to $150,000. By using the lasers, this fiber system, they've compressed the price down to about $40,000, which is a considerable savings. So it's something hopefully that will be turnkey, that they can just put in a lab and people can start using it, which is very attractive to chemists. So what's the experiment? What are we going to do with it? How are we going to demonstrate that this laser is actually something that we can use as chemists? And so I propose that we do an experiment called a T-jump experiment. And a T-jump experiment is, this is just a cuvette. It's just a cuvette with a sample in it. And so here's my sample. And what I'm going to do is I'm going to take a pump pulse from a laser and I'm going to excite the sample. And so when I excite it, something's going to happen to it. Okay? Over time, that sample is going to relax back down to its original state. And what I'm going to do is I want to monitor the changes in that sample with some type of probe. And my idea is to use this fiber laser as the probe. Okay? And so, let me see if I can go back. So here's this laser sitting on a table somewhere. It's producing these pulses at 10 microns, and I'm going to build a spectrometer now that I can use these pulses. And so I need a pump. We've had a lot of different ways that we've thought about pumps, but basically we want a pump that will pump the sample at about 500 nanometers. So we're going to excite the sample with those pulses. And then we're going to bring in the probe from the fiber laser, pass it through the sample, and then use some type of detection signal to detect it. Now, because of the fact that infrared pulses, the detection systems are pretty slow, meaning the fastest I can really look at something on the time scale of it happening is in like the microsecond region, microsecond to millisecond, which in terms of femtosecond world where I live, that things happen really quickly, that's really long, milliseconds to microseconds. So to find a chemical process that occurs on that scale was a real challenge for me. And so what I proposed to do was to study how molecules that are interacting together might melt. And when they melt, how do they reform the solid? And so I proposed to look at a benzene and hexafluorobenzene mixture. Benzene is just a ring of carbons. There's carbons, 1, 2, 3, 4, 5, 6. I don't know if you can see that. A ring of 6 carbons. And then hexafluorobenzene is a ring of 6 carbons, but now you have fluorine connected to it. Where in benzene down here, we don't show it, but there's hydrogens connected to this. And this, a 1-to-1 molecular ratio of these two molecules forms a really strong complex that actually exists as a solid, it's all wet, as a solid at room temperature. So I can pass this around if you want to see, or you can just look at it later. It forms a nice kind of clear crystal, and its melting point is very close to room temperature. So it can quickly go from a liquid to a solid just by a simple temperature change near room temperature. And what's unique about it is that both benzene and hexafluorobenzene by themselves are liquids at room temperature. So it's unique in that when it does combine, it is a solid at room temperature. And so one of the things I wanted to show was this is just a phase diagram, this picture here. This is just a phase diagram. All we're showing is we're plotting temperature on the y-axis versus the mole fraction of the hexafluorobenzene. So the mole fraction just means how much of the hexafluorobenzene is in the sample compared to the pure benzene. So 0 point, that's where I have pure benzene. And what this graph shows is that at this point, at 5.4 degrees Celsius, that's where benzene melts. As I start adding hexafluorobenzene to the sample, if I have pure hexafluorobenzene, what the graph shows is that it melts at 5.0 degrees Celsius. Notice right here in the center, it's the highest point. And so what we're seeing is that it was reported in literature that the melting point was 23.7 degrees, and we actually measured it at CSU to be 24.11. We were pretty happy how close we got it. And so we see that this compound will melt very close to room temperature. I know you guys don't really care about it, but there are these points down here, and that's just to do with this eclectic temperature, and so I won't go into that, but just note that it's kind of interesting, but not really. Okay. I did want to show the actual data because this is one of my few slides of actual data. And this is the actual data that we took to determine what the melting point of the complex was. And so this is, we actually take this data using this differential scanning calorimeter instrument. And this is just a plot of, on the y-axis of heat flow, and on the x-axis temperature. So we start at you know, like minus 12 degrees Celsius. We go along, we see this little peak here, we keep going, and then we see this big peak around 24 degrees Celsius. And this big peak is due to the melting of the complex itself. The little peak here is because as much as we would like to have a complete 50-50 mixture, we just can't get it completely 50-50. So you always have a little something that's not the complex itself. But we can work on that, okay? All right, so now we do have something that is possible that we could study. Just some background about these molecules. Both of the molecules are what we would call symmetrical, meaning that if I drew an axis here and I looked at this fluorine, there would be one mirror image of it on the other side. And so both of these are symmetrical molecules, and they don't have any dipole moment, meaning they don't have a net charge over the molecule. But if I look at the molecules individually, they do have what we call a quadrupole moment. And that's just the way that the electrons are distributed in the molecules. And because the hexafluorobenzene has these fluorines on it, some of the electrons spend more time on the outer edge than they do in the inside. Where in this case where we have the hydrogens, it's the exact opposite. So we see that the quadrupoles have exactly opposite signs, and they have basically the same magnitude. So we're attributing this strong interaction between these two molecules to this positive and negative quadrupole being attracted towards one another. Okay, what do they look like? There's actually been crystal studies where they've actually determined the crystal structure, and so what we see is that the molecules stack where you have, you know, the benzene, hexafluorobenzene, benzene, hexafluorobenzene, so you get these long columns, infinite columns that kind of just alternate and intertwine with one another. There's actually been some calculations that have been done with computational chemistry to determine exactly how these two molecules interact together. We could think of it as a sandwich model where they're stacking directly on top of each other. We could think about them interacting in a T-shape. Obviously, that's what the picture shows. And then there's another type of T-shape where you can have the hexafluorobenzene on top, etc. And then you have this slipped parallel where they're slightly off axis from one another. And when you calculate the energies of these systems, the more negative the energy, the more stable the system. So what we find is the sandwich and the slip parallel are the two most stable, which goes right along with what we see for the crystal structure. However, the slipped parallel actually has a little bit more stability, you know, about 0.3 kilojoules per mole, a little bit more stable. So hence, they're not perfectly straight, these columns. They are kind of slanted. And so both dispersive, we find that both dispersive and quadrupole electrostatic forces play important roles in these interactions. And so those are the type of interactions that I'm going to study with my spectrometer, or I hope to study. So the proposed experiment is to use a sample, the benzene hexafluorobenzene complexes, 1-to-1 complexes. I'm going to excite it with the light. I'm going to have something change. Basically what's going to happen, it's going to be a solid. I'm going to heat it up so it melts, and then I'm going to watch it refreeze over time. Now, how am I going to probe it refreezing? I want to use that fiber laser in the infrared. It has a 10 micron wavelength. 10 microns is 1,000 wave numbers. And so as a chemist, I think about molecules vibrating in terms of wave numbers, which is just another unit, like nanometers or micrometers. And so I just want to point out that the benzene itself has a CH stretching vibration. In the liquid, it occurs at about 1038 wave numbers, which is 10.38 microns, okay? And then what we see is when it becomes a solid, it splits. The peak splits into 6 peaks. I also find that if I look at the complex, the hexafluorobenzene-benzene complex at a liquid state, I see 1 peak at 1038 wave numbers. And in the solid, I actually see 2 peaks, and they're very strong. So the idea is that we're going to melt this sample. We're going to have some type of absorption at 1038 wave numbers, and then over time, as it refreezes, this peak is going to split, and it's going to grow in intensity. So I can monitor that with my fiber laser, that change in absorption. That's the idea. So, how much energy is it going to take to melt this thing? That was our big dilemma. How much? So we did a lot of calculations. I won't go into a lot of detail, but what happened was we found that we needed 375 microjoules per pulse. Doesn't sound like a lot, does it? Microjoules. But in the world of laser chemistry, it can be a lot. So just using the fiber laser itself as my pump wasn't going to be enough energy, because I was getting pulse powers about 5 nanojoules per pulse. Way, way too small. Wasn't going to melt the sample at all. So one possibility was, what if I used a laser with a lot of power and I excite something in the sample that will absorb a lot of energy and then transfer that energy to the hexafluorobenzene mixture. And so one of the proposals that we really focused on at the beginning was to actually make gold nanoparticles, dissolve them in our complex, and then excite the gold nanoparticles using an indium YAG laser. These are very common lasers. We have one already in the lab. It produces 100 to 200 millijoules per pulse, 100-fold more energy than I need, and it's at 532 nanometers, right in that 500 nanometer region where gold nanoparticles will absorb. So it was looking good. And so that's where Shanice comes along. Shanice Butler, one of our chemistry majors, is going to graduate this year. She received a NSF-REU fellow to come out and work with me at CSU in the summer, and her job was to actually synthesize the gold nanoparticles and then get them into the solution that we wanted to study. So she came out, and the first thing that she did was she actually synthesized the gold nanoparticles in water. And the way that she did that was she uses this hydrogen tetrachloroaurate trihydrate. I hate pronouncing these things because I just like to look at the structures. But it's a gold molecule connected to 3 chlorines, or 4 chlorines, and there's a hydrogen, and then there's some waters attached to it. So it's just something that you can buy off the shelf, put it into water, it dissolves in water, and you've got gold in water. But then we're going to reduce it and form these nanoparticles. What do I mean by a nanoparticle? Well, a nanoparticle is something that has a couple hundred to maybe 1,000, couple thousand gold molecules that have come together to form a small particle. It's nano in size, meaning that it's smaller than visible light. Visible light has wavelengths of about 400 to 800 nanometers. So these particles are smaller than that. Actually, the particles that Shanice made were 10 nanometers in diameter. So they're very small particles that don't scatter light because they're so small, and they will actually be in the solution. So she made these complexes, and here's a sample vial that she has, and you can see that it's kind of blurry. But what I want to point out is that it is a clear solution, meaning you can see right through it. But the hexafluorobenzene in the benzene's clear, and notice now it's colored. It's purple in color, meaning that we have something in there. Hopefully it's the nanoparticles. We proved that it was the nanoparticles. One of the ways that we proved it was by looking at the UVVis spectrum of the sample, where we were just plotting the absorption of the sample, where it absorbs a wavelength of light versus the wavelengths. So what we see is that at 530 nanometers, this sample strongly absorbs light. And hence, that's why we're seeing this purple color now. So that looks good. And then the other thing she did was she actually measured the size of these particles using dynamic light scattering. It's just a technique. It's an instrument we have in the lab. She puts it in the instrument. It takes a little finesse, but you can get the data. And what she determined was that the radiuses of these particles, she looked at 4 different samples. They ranged from 7.8 to 13, and the average was about 10 nanometers in diameter, with a standard deviation of about 2.3, 2.4, good enough because of the size and just the nature of the instrument itself. We're pretty confident, though, that on average we're looking at particles that are 10 nanometers in radius, so 20 nanometers in diameter. So, great, we've got nanoparticles in water. Do we want nanoparticles in water? No. We want them in benzene and hexafluorobenzene. Water and hexafluorobenzene and benzene are totally different creatures. Water's polar. It likes things like gold nanoparticles. Benzene, not polar. Doesn't want to have something that's polar in its environment. So what are we going to do? So Sinead went into the literature and she found a nice synthesis where you actually use a surfactant molecule that's slightly soluble in both water and oil. It happens to be this DDAB molecule that's shown right here, and it's didecyl dimethyl ammonium bromide. So it's got an ammonium group and these two long carbon-hydrogen tails. So here's the part that likes water, here's the part that likes something like benzene. And again, she does a basic synthesis, she forms a gold nanoparticle, but now surrounding the gold nanoparticle are these surfactant molecules. And so there's like a shell of surfactant now around this nanoparticle. And when you put it in the UVVis spectrum, she actually saw a spectrum. Yay, it was absorbing. It absorbed around 528 nanometers. A little bit different wavelength, but the sizes were slightly different. So we can account for the wavelength based on the size of the nanoparticles themselves. And so, even so, these gold nanoparticles with the DDAB caps, we called it, were more stable in water than benzene. That's what we found. So here's just a sample of her sample. Here's the water layer down here where she has the gold with the DDAB caps on it, nice purple color, and she's got benzene on top. Benzene's less dense, so it won't mix with water, so it sits on top. And you can sonicate it, you can centrifuge it, and guess what? It looks just like that. So we were having difficulty, well, she was having difficulty getting it into the benzene layer. But after doing a couple tricks and going back into the literature, she found that if she added hydrochloric acid, she could actually strip or change the cap from being hydrophilic, meaning liking water, to something that's hydrophobic, something that would like the benzene. And so you can kind of see from the picture here, what it did was it caused the head groups of the surfactant to come around the gold, and then the tails to fan out. And so these tails will allow it to dissolve in the benzene. And guess what? She got it to mix. And so we were actually able to move the gold particles into the benzene layer, which was great. And so we just used a pipette and sucked that off, and we were actually able then to mix it with the hexafluorobenzene. Yep. To prove that we did get gold nanoparticles in the benzene, you can see here's it's a visible near IR spectrum of benzene. So it's visible, meaning that it's from 400 to about 800 nanometers, that's the visible region, and then we actually scanned up to 2000, or that near infrared region. Basically because we were interested in these overtones of benzene and just looking at maybe we could probe that at one time. So that's the only reason why we're showing this. But you can see when there's no gold nanoparticles in there, there's no absorption around 500. But when she adds the gold nanoparticles, she gets her nice little peak there, showing that we do have it in the solution. And she also obtained visible and near IR spectra with the gold nanoparticles in the benzene hexafluorobenzene mixture. Again, we're looking at two different spectra, one from a small path length and one from a larger path length. Again, I'm plotting absorption versus wavelength. And you can see with the small path length, I just get a little bleep at 531, but when I do a longer path length, I see more absorption. So I get a larger peak here at the 531, showing that the gold nanoparticles are dissolved in this solution. Okay. And if you take the infrared spectrum of the gold nanoparticles in benzene, what we see is, there's that peak, that 1030-ish wave number peak that's there in the liquid that we would expect to grow and split as this solution became a solid. And so everything's looking good. Notice there's a big water peak here, for those of you who know what you're looking at. But this vibrational stretch here that's being absorbed is water, and so we did have some water in our sample that we had to work with, and so there was some finessing to do, but we were able to do it. And we could actually get the gold nanoparticles into the complex, and it would stay in the complex for a couple days. So that was stable enough to actually run some experiments. Okay, before I show you the new plan, something happened. The thing that happened was that, yay, we got it into the liquid benzene, hexafluorobenzene. And then we froze it. And then we thawed it. And there was no more gold nanoparticles in the solution. Because of the nature of that interaction between the hexafluorobenzene and the benzene, it's so strong, it just squirted out those gold nanoparticles. And it caused, I think there was some type of reaction with the surfactants, and those gold nanoparticles just fall out of solution. And so it wasn't going to work. It's October. It's not going to work. And so, very disappointedly, we had to come up with a new plan. And so right now we're in the process of doing the new plan. The new plan is that, we still want to use gold. And so our idea is, let's take a gold mirror. The mirror is only about 1 inch in diameter. Let's use that surface to reflect off some laser beams. But if we use the right laser with the right wavelength, some of that energy will be absorbed by this gold surface. So our idea is to take the gold mirror, lay it flat, take the hexafluorobenzene, benzene mixture now, put it on top of the mirror. We just need a thin layer of it anyway. So we'll take a drop, put it on the mirror, let it spread out. We have a holder that can keep the temperature pretty constant, so it'll be a solid on that mirror, a solid crystal type structure. And then what we can do now is bring in our pump laser, which is that neodymium YAG laser at 530 nanometers. And then we can probe it with our fiber laser. Now some of the light is going to be absorbed by the sample itself. And so what we're going to see is the light that wasn't absorbed by the sample. And by detecting that light, hopefully we're going to be able to explore then those interactions between the benzene and the hexafluorobenzene. And so I worked closely with one of Nancy's graduate students, and he's actually doing some tricks to get the neodymium YAG beam from one room to another room, and actually setting up this experiment. We hope to do it this summer. So that's kind of where my project stands at this point. I would like to acknowledge, of course, Nancy Levinger and her group. She's been a great collaborator for many years. And then now getting a chance to work with Randy Bartle and just seeing how they do it over in engineering department is pretty interesting. I do want to thank Shanive, because obviously without her work with the nanoparticles, who knows where I would be at this point in the project. The project is funded by the National Science Foundation, and an NSF REU did support Shanive over the summer. And of course Agnes Scott for allowing me to have a sabbatical and getting this opportunity to go. And here's just a picture of Shanive with one of the other guys in the REU program standing by her poster that she gave this summer at CSU. So thank you for listening and coming. Yes, do you have any questions? I'd be happy to talk a little more about it. So yes, you'll see that there's shockingly little data. I will just say it right up front, but you know, it's the process. I feel like I'm just getting restarted back with a new project, and it's just the process. So hopefully I'll have data soon. That's my goal. Yeah.
So I'm obviously the laser geek, so I'm still back to the laser.
Yeah.
But do you do other wavelengths with that, or they do?
Yeah. Oh yeah.
The
Okay.
ytterbium is not up to micron.
Let's see.
You know, 'cause I think we should get one.
Oh, yeah, yeah, $4,000. I mean, $40,000. Yeah, nothing, right? Yeah. Okay, so this laser produces about 1.5 micron pulses. Okay, and so then we amplify it, and then what we do is we put it through a difference frequency generator, and so we can get a number of different wavelengths from that. And that's why you can get the 3 to 10. And even the amount of energy that you actually put into the lasers and into the amplifying systems, just by tweaking the amount of energy that you're putting in from the diode lasers, kind of tweaks the wavelengths. So you have some tunability with this laser as well. Yeah. So, yeah.
So in your experience, when you try all this stuff and it's going great, and then you get somewhere and it's not going to work.
Yeah.
That happens. Probably a lot of this, but it certainly happens in that. Like, we worked for a long time, making all this progress, and all of a sudden you realize everything you just did for the last months or years is not going to work.
Yeah.
And generally, you can't, in math, there's not a way to publish that. It might be helpful, but
Yeah.
to other people, so they won't make the same mistake.
Yep.
Generally, you can't. So is your result there when you freeze it doesn't work? Is that something that you can publish?
No. Hence, this is a sad story. Yeah, no, you can't. No. Nope.
You can always laugh at other people.
Right. Exactly. Or we can have our own club and go to the back room and cry.
There is a new journal that actually addresses that issue, and it's targeted for chemistry, but it's chemical reactions that you can't repeat even though they're delivered to you. And so you can write your attempts to repeat published research that failed. And basically it acts as a warning that maybe this work is not truly reproducible. There is now a journal published in Australia. It's an international journal to deal with that very issue.
Yeah. Well, this is new work, though. Nobody's ever tried this before, so I could put it out there and say we did it, and then have somebody come along and dispute it. I don't know how kosher that would be, or good.
So, your detection systems, I guess, are behind your excitation systems. Is that?
Yeah. Yeah, what happens is, let's see if I got the picture here. Yeah. So you can see the pump pulse comes along, and we actually kind of block it because we don't really care what the pump's doing, because the pump, we're just using it to excite the sample. So it is that probe, as it goes through the sample, we're going to detect it directly as it comes past the sample. So we're looking at a transmission signal.
I mean, I guess your probe has the capacity to look at things on a real molecular time scale.
Mm-hmm.
That your detection system can keep up with that?
No, it can't. So what happens is you look at your signal, and it's just got a really long rise time, and so everything that's happening at that rise time is just blurred out. And so the idea is that as it refreezes, it's going to occur on that microsecond to millisecond time scale, and so I'll be able to see how those absorption profiles change as it refreezes.
I guess to take full advantage of this laser to look at other reactions, there needs to be advantage.
Yeah, and there is some ideas, because one of the things that you can do is you can use the delay stage, or the length of time that it takes for a pulse to get to the sample. So you can pump, and then you can bring in the probe right after or a little later, and then just keep sitting there and looking at that signal at that difference in time, or difference in length of paths of those two beams. We didn't really want to do it with this system because of the fact that we would need a baseball field to get the delay, but we have an idea of winding around the pulses around a circle a number of times to put that delay in, so we could actually shorten that time. Yeah. So there is plans to think about how to do that. Okay. Yeah, that was always the big concern, was that even if it was it was going to affect that structure. And hopefully, because we're looking at an ensemble of molecules, the majority of them would be minimally affected by that. So really the new plan is better, because the new plan, we've avoided that problem. Yeah.
I guess you'll have melting occurring.
But it's only going to happen at the spot size, pretty much. The spot size of the laser, which is, you know, what? Oh gosh, 50 nanometer, 100 nanometer spot size. So the melting is just going to be right at that spot that we've actually excited that laser.
But I guess the heat's being transferred from the gold surface, so you might get, are you worried about differential melting of your
Yeah.
drops?
Yeah.
Of depth?
Yes, and that's actually one of the things that the graduate student is doing right now, is trying to see if we can actually do some calculations to predict what that differential melting would look like. Yeah, that's exactly right. And so part of it's going to be, you know, taking into account the depth of that layer, and so knowing what region we're probing is going to be very critical. Yeah.
Yeah, you just want, I guess, your sample.
I just, yeah. Yeah. And see, and hopefully see some changes that we can correlate. Yeah. Yeah. Okay.
Your gold particles, are they flecks of gold metal, or are they molecular gold clusters for
They're-
that size?
They're molecular gold clusters at that
Can you
size.
try smaller gold clusters?
Sure, we have, yeah, depending on your synthesis, you can control the size just by changing the pH a little bit, and yeah, changing the pH, that type of thing. You can control the size, and you can get much smaller, you can get much larger. So there's a wide range of sizes that you can get with this reaction. Okay. Well, thank you all for coming. I really appreciate it.